Does the recording start?
Yes, I heard it start.
Okay.
It didn't hear anything, but
Do you see the notification at the top or on the top left, the little red dot?
all right. So, hello, folks. Welcome to the Graphics Programming Virtual Meetup. Today, we will continue reading this book, Physically Based Rendering, and we are in chapter 6. So, shapes. So we will talk about geometric primitives such as spheres and triangles. PBRT hides detail about the primitives behind a two-level abstraction. There's a shape interface and also primitive interface, additional non-geometric information, such as material properties. Okay, so this chapter will only talk about shape, and primitive is chapter 7. So a shape is this. So just remember that PBRT use this tagged pointer stuff because GPU does not allow kind of C++ polymorphism. So let's use this. They don't have any special case for triangle though. Like triangle is just like that. Does that mean all triangles need a back pointer to a mesh or something? It sounds very wasteful, but whatever. Okay, and all shapes need a bound, so we have A, B, B. And so just we have this function returns A, B, B. Shapes must also be able to bound their range of surface normals. Interesting.
But yeah, not heard of something like that before.
Yeah.
Interesting. I guess like if it was a solid mesh, then wouldn't it be like basically every axis around it?
Yeah, so definitely not mesh, but yeah, for a triangle or
Yeah,
something like.
a single triangle, yeah, I can see a single direction and some of
Yeah,
the other
but
primitives, but
for a sphere, then it's everywhere.
yeah,
I feel like this is for lighting, but
it most definitely is, but
but
how it would be used is be interesting.
all right, yeah, using lighting calculation. Yeah, when a shape is emissive. So there's a ray bound intersection with like bound 3 intersect P to determine whether there is a ray box intersection or not. Intersect P should be intersect point. So intersection of three slabs, where a slab is the region of space between two parallel planes. I struggle to understand what that means. Anyway. Like, yeah, but this image, I feel like it's clear enough. I still don't understand what this sentence means though.
The image is like the 2D case.
Yeah,
So you see x0 and x1 and y1 and y0.
yeah.
They're parallel
Oh,
lines.
yeah, I see.
Yeah, so that each pair of lines is how they describe
Yeah.
a slab in 2D space. And then in 3D, it's you add a third set of parallel lines, and then that defines a box.
You start with a parametric interval that cover range of positive t. Along the ray where we are interested in finding intersection. Yeah. Yeah, we compute the parametric t position where the ray intersect each axis aligned slab. Yeah. I have to admit, for this particular code, I used to just copy and paste, so I never understand how it works. Yeah, so basically it's just doing intersection of intervals starting from 0 and t max, and then we'll talk about it later, like update intervals, then what's hit 0 and hit 1. Just a range. The origin is inside the box, then hit 0 will be 0. Yeah. For each pair of the plane, this routine need to compute two ray plane intersection. Yeah, and this just the same deal of like we have an equation like this, and then we just substitute the ray equation, which is like point origin plus t direction, and we just substitute it to x and y and z, and then do some algebra and then get this. Okay, and y and z component of planes normal are always 0 because we are talking about the x-axis. So BC are 0 and A is 1. That's why ABB is simple. The plane's D coefficient is -0. I kind of forget how to interpret this thing. Like, I think ABC is like the normal, but what is D? Kind of forget how to interpret this. But anyway, but we can use this information to get this. Okay, so they don't want to do multiple division of the same thing, so they do an inverse. And yeah, if it is 0, then we have infinity. And it will still work. Yeah, where is Pmin and Pmax calculated? Oh, this is just a bond. And yeah, we have a new range, and if this new range is empty, then we just return false. But another floating point related subtlety here. Yeah, we can get nan, which is really bad. So if any of them is nan, then T0 and T1 will not ever take on a nan value, but will remain unchanged. Okay, so that's those two lines. Oh, that's why they have. No, because if it's NaN, then the comparison will return false, and then we will go to here. Let's see. I feel like this need a comment, because definitely not easy to see just by looking at it. Yeah, also has a specialized intersect method that takes the reciprocal of race direction as additional parameter, so it doesn't need to be calculated each time. Also take a pre-computed value that indicate whether each direction component is negative. If the redirection vector is negative, then the near parameter intersection will be found with a slab with the larger of the two. Oh, yeah. So basically, we don't need to do this. Wow, 15% of performance improvement. That's cool. Yeah, shape provide two intersection. First intersect return geometric information. Like this. I like that they use optional in this version instead of alt parameters.
Me too.
Yeah. Yeah. Tmax define the endpoint of the ray So if we already have an intersection and then we do another intersection test and find a t-value greater than t-max, we need to ignore that intersection because it's behind. Yeah, the closest one should be reported. Yeah, shapes are responsible for transforming the ray into object space because the A, B, B are all in object space. Wait, maybe A, B, Bs are not, I don't know. But the shapes are definitely in the object space. Yeah, this is just a simplified version which returns a bool, which is useful for stuff like shadow rays. Yeah. Because it's cheaper, but less information. Intersection coordinate space. Yeah, for some shapes, intersection routines are most naturally expressed in the object space. For example, sphere. Other shapes like triangle can transform their representation into the render space and then perform intersection there. Yeah, we can just use this transform method, transform class. And yeah, how does it impact the distance? Using the property of transformations, it is possible to show that the t distance to the intersection is unaffected by transformation. With the object intersection is this, and if we apply the inverse transformation, get this. So t is correct no matter what. I didn't know that. I remember in one of my previous retracer, I discarded the t-value and after transform, I recalculated.
Yeah, I had no idea this works.
Yeah. Oh, if the object's race direction has been normalized after transformation, then this will no longer be the case. So yeah, PBRT does not normalize object space race direction. Oh, I see. Yeah, that's why probably mine didn't work. Siding is okay. Basically, PBRT does not support back face or front face because it's ray tracing and don't matter that much. Also, it can lead to a physically inconsistent scene. Area light. So in there, we need to calculate the surface area. Yeah, using as emitters, we may need the sampling method. Both named sample. So we give it a uniformly distributed sample and then it returns a sample on the shape. So point and also the PDF. So shape has a PDF method that returns the probability density for sampling. It's mod is useful for MIS. Detail is that the implementations are allowed to assume that the provided point is on the surface. And I think this can also use this. I don't know how this is implemented though. Maybe this is reversed. A second shape sampling method take a reference point which the shape is being viewed. Only sample the portion of the shape that is potentially visible from the point. And so we pass additional information. Which has a point. Also, where we have two normals. normal and shading normal. I think we will probably talk about this later. Oh, is this like the geometric normal? This is like normal at a specific point.
Yeah, like interpolated
Yeah,
between vertices.
I see. What a bunch of constructors. Okay, I missed that. This can represent numerical uncertainty. But for code that doesn't need that, it can just cast it back to normal point. Okay, another. Yeah, just for the like floating point uncertainty, it needs to offset a little bit. All right, I think we are done with this section. Any comments before we end this? Okay, let's stop recording.